Hi guys. Okay, second half of Unit 2. So, idea here, let me pull it out of the sleeve, then we won't get that glare. So we're going to start by talking about light and waves. So first off, a couple things. We need to look at this idea and understand this concept that light is both a particle and a wave, and so it has that dual nature, and that we are going to start by looking at the wave nature of light. Okay? And so we have some main ideas here. Energy moves in quanta. It makes tiny little jumps. Okay, and then the packet of energy called a quanta. Einstein came and he called that a photon. Okay? And so we had a couple of things that we ran into. Okay, so first we need to remember that the nucleus contains the protons, and that the electrons are negative, and then we have our positive protons. And so why aren't electrons just falling into the nucleus if we have that electrostatic attraction? And it's because the electrons are found in fixed energy levels, and they make those tiny little jumps in energy to different energy levels. Okay. Now, before you make the connection between the two, let's look at the wave nature of light. Okay? So a light is part of a huge electromagnetic spectrum. And so this spectrum goes from like radio waves all the way to gamma. And so it is just a small sliver of this huge spectrum. And so we call it electromagnetic or electromagnetic radiation. And these are all waves. They're all the exact same thing. They just have different wavelengths. Okay, so wavelength is two equivalent points on a wave. Okay? The distance between them. So it might be from trough to trough, or it might be from peak to peak. Frequency. Frequency is how many waves pass a given point in 1 second, like a specific time frame. So if we were standing on the edge of a pier and we're watching the ocean waves come in, and every second one ocean wave hit the dock, that would be a frequency of 1 wave per second. Okay, that's frequency. Now, notice if these two waves are traveling at the same speed, and so they're traveling, and given a certain amount of time, they hit an equivalent point. Because this wavelength is longer, it's going to have lower frequency. There's going to be less waves hitting that point in the same amount of time as our high frequency wave here with short wavelength. Short wavelength means high frequency, long wavelength means low frequency. And that's expressed in this equation. Speed of light, and so all electromagnetic waves travel at the same speed, which is 3 times by 10 to the 8th meters per second. That speed is the wavelength multiplied by the frequency. Okay, and start getting used to these symbols here. Okay, so we have wavelength, which is lambda, frequency. Okay. Now, here's the other important thing, is we need to relate this to energy. Okay, so it turns out that long wavelength is low frequency, which is low energy. And if we have short wavelengths, then that's high frequency, high energy. Let's put some names to this. We have proportional and inversely proportional. Okay? Proportional means when one thing gets larger, the other variable gets larger. Or if one gets smaller, the other one gets smaller. Okay, so those are proportional. So we could have this idea of like wavelength as a variable, frequency as a variable, and energy as a variable. Okay, and when one gets big, if the other one gets big, then they're proportional. If one gets small and the other one gets small, then they're proportional. Now, inversely proportional, though, is when one gets big, the other gets small, or if one gets small, the other one gets big. That's inversely proportional. So here's the important concept that you need to know. Wavelength, big wavelength, equals low frequency. One is big, the other one's small. So those are inversely proportional. Let's check it here. We have short wavelength, high frequency. So when one is little, the other one is big, inversely proportional. Now frequency and energy though, we have low frequency, low energy. So one was small, which made the other one small. And so those are proportional. High frequency, high energy, so those are proportional. And then the last jump what we can make here, wavelength and energy. Big wavelength, low energy, inversely proportional. Short wavelength, high energy, inversely proportional. Okay, here's the spectrum that I was talking about before. That electromagnetic radiation is just found on this spectrum, and it goes from radio waves to gamma, and this tiny little fraction of it here, that is visible light. So visible light is the exact same thing as a radio wave or a gamma ray. The only difference between them is the wavelength. And if we have a different wavelength, that means we have a different frequency, which means we have different energy. Okay, let me check time. Yes, moving right along. So let's think through the energy portion of this. Wavelength 3 times by 10 to the 4th. Okay, and then 3 times by 10 to the negative 14. So this is significantly smaller. So this is our small wavelength. This is my large. Okay. And then here, 10 to the 4th for frequency, 10 to the 22nd for frequency. So we call this low frequency. We call this high. And notice, energy is a part of this, right? Saying energy slash frequency increases. And we can relate this because frequency and energy are proportional. So frequency and energy are proportional. And so that's why we can say, well, if energy increases, then frequency must increase. Or if frequency decreases, then energy must decrease. Okay. Now, I also want you to look at this concept check here. So if you were absent, you missed class, hit pause and give this concept check a go, and then come back and let's look at it. Okay. Compare speed, frequency, and wavelength of a microwave and a gamma ray. How are they similar? Let's see. Speed. Every single wave on the electromagnetic spectrum travels at the speed of light. Okay? And so that speed is 3 times by 10 to the 8th meters per second. They all travel with that speed. Okay? How are they different? Well, their wavelengths are different. Their frequencies are different because the wavelength is different, which also means that their energy is different. Okay, and let's make those determinations. So we're comparing microwaves and gamma. So there's our microwave range, and then there's our gamma range. Okay, so we already said this is a large wavelength. So microwaves have a larger wavelength. Gamma rays have shorter wavelength. Okay, frequency. Microwaves, if they have larger wavelength, that means they have lower frequency. Gamma, if they have shorter wavelength, that means they have higher frequency. And then same with energy, lower energy, higher energy. Okay. Arrange the following types of electromagnetic radiation in order from longest to shortest wavelength. Well, here's our longest wavelength. And then there's our shortest wavelength. So we'd have radio, microwave, infrared, and then gamma, according, comparing that list. Arrange the following colors of light in order from lowest to highest energy: yellow, blue, green, and red. Okay. Well, let's remember, we know that red is the longest wavelength, so that would be the lowest energy. And we want to go from highest to lowest. Okay. So that would put red at the very end. And then we have our rainbow colors, our Roy-G bit, right? So we have red, orange, yellow, green, blue, indigo, violet. Well, red is the longest wavelength, violet is the shortest wavelength. And so that would mean that this is the highest energy and that's the lowest energy. So highest energy of these ones would be blue. Okay, then we would have green. So we have blue, green, and then yellow, and then red. What is the speed of the electromagnetic wave? Well, we already talked about that. The electromagnetic waves, all of them travel at the speed of light. For EM, or electromagnetic radiation, has wavelength increase frequency, saying if our wavelength gets bigger, then what happens to our frequency? If wavelength increases, frequency decreases. Okay, so that's the first day's materials. Let me know if you have any questions.